All right, welcome back. Let's get straight to it. So here we have our little, um, I don't know, blackboard, notepad, whatever, and we're going to get started with section 1. I'm going to try to use the power of technology. Bam! Look at that. I can't do that on a blackboard. And also can't do this on a blackboard. Hey! I love that. It feels like black magic. All right. So introduction and key challenges. So first I want to draw a picture. I promised you guys a picture. I'm going to draw a picture. Change the color of my pen to black. If I can see black. Oh, here it is. All right, and I'm going to draw our parallel lines. Okay, so making this big. Alrighty. And now I'll draw an arc that spans these lines. And it's going to be pretty free. I'll start off here and just come up like a sort of like an S shape. Maybe it looks like that. Who knows? Maybe it looks like this. Can look like a lot of different things. There are very few restrictions on the geometry of our arcs. Okay. But these are the parallel lines, and this red curve is the main object of study. Okay, so let me write down what the equations are for these two flows. The first one is the curved diffusion flow. Okay, now this red arc has a name. Call it a Greek letter. Call it gamma. Mathematicians love Greek letters. I love Greek letters. It's just a really nice looking, convenient language to use for mathematical objects. All right, let's keep going. So basically, we need to prescribe the evolution of this curve. So let's do it. We go time derivative, and I will just, so this is a differentiation symbol, so this is the change in time, and now I put a little perpendicular symbol up here to mean in its normal direction. So along this curve, you've got what's called a frame. Basically, let's draw it here. There's an arrow. Well, I think I can actually make an arrow. Let's make it a little bit darker. There's a normal direction, and it can be pointing up or down. These arcs don't have any inside or outside, so whatever we do has to be what we call invariant under changes in orientation. And we can also prescribe sort of the tangential direction as being either going from left to right or right to left. Because we do have a proper notion of left and right, we can say that the parallel line here is left and the other one is right. Okay, now here the frame might be looking like this, but the idea is that these are normal vectors and tangent vectors at each point, and they have certain names. So in this series of talks, we're going to call the tangent vectors tau, another Greek letter for you, and the normal vector nu, another Greek letter for you. So maybe you could also view these videos as a way to learn some Greek, even though I am not qualified to teach Greek. Okay, so what we're prescribing is the normal change in the normal direction, because if you change in the tangential direction, then that's okay, but it's really just moving points along these curves, and except at the boundary. On the boundary, because we are stuck on these parallel lines, the tangential movement has to be 0. Anyway, so we prescribe the normal movement because that will change the actual shape of this curve. For curved diffusion flow, we move in this kind of direction. So we take minus 2 derivatives of the curvature. Okay, and yeah, this is in the normal direction, so we'll put a normal vector there. Oh, I know you can't see it. I know you can't see it. It's all right. It's all right. There we go. It's all better now. Okay. But is it really better? So this curvature is, like I said before, a measurement of the bending. If you already know what it is, then that's good for you. But if you don't, then it depends on derivatives of the curve gamma. Basically, you can think of it as the normal component of the second derivative. Let me write it down. So we're going to say, recall. The curvature scalar is the normal component. So this means component. This is what we call an inner product. It's the normal component of two derivatives of the curve gamma. Now, if you have done some high school physics, this will make a lot of sense to you because the second derivative of anything is its acceleration. And so what we've got here are derivatives with respect to the parameter s, which is the arc length. So this is like the second derivative, the acceleration of the curve gamma with respect to its length along the curve. So as you measure the distance along the curve, you take a derivative, and then you take another derivative, gives you an acceleration vector, and that will tell you how it's bending, how the curve is bending. And then you only take the normal component of that, because the tangential component ends up being 0. So that's really the most important piece. Okay, and we call that the curvature scalar. So this little k here is called the curvature scalar, and the curve diffusion flow is moving the curve in the direction of the acceleration of the curvature scalar. Why would you want to do that? It's actually a very well-known equation. It comes up in physics, but I'm not going to survey where it comes from. You just have to trust me that this is a this is an interesting thing to look at. Just trust me. All right. The other flow is algebraically quite similar. Okay, so well, let me just introduce a little bit of shorthand here. We're going to use a subscript to denote the derivative, like this, ks. We're going to use a subscript to denote the derivative, and that will help us shorten our equations. Now the free elastic flow, FEF, we're going to talk about that as well, and this is, yeah, like I was trying to say, algebraically it's quite similar, but in terms of how it's written down and where it comes from, it's very different. Okay, so again, it's a prescription of the normal derivative of your family of curves, and you have, oh sorry, this is two s's. You have again this term KSS, like the curve diffusion flow term. We call this a diffusion term. And then you have, in addition, a reaction term, which looks like 1/2 k cubed. Okay, now where do these things come from? Basically, the curve diffusion flow comes from a reduction in length of the curve in what we call h-1. That's not completely true. I will talk a little bit more about that in the next one, but it's morally correct. The free elastic flow comes from a reduction of the total bending of the curve in what we call L2, and that is not that's not dishonest. That's actually true. So with the h-1 thing, it's a bit dodgy, but we still say it. The free elastic flow, reduction of bending in L2, true. Okay. And now, what do we prescribe on the boundary of these curves? What do we say? We have boundary conditions as follows. So we set, we enforce that there's a angle condition on the boundary, so it has to actually touch the boundary, and it has to do so at right angles. So let's just write, let's do a symbol for that. Right, perpendicular touching, let's just say it like that. In math lingo, we might call this a Neumann condition. Neumann. And now, because our evolution equations have so many derivatives, we need another condition. And what we use is called no flux. The no flux condition is called that because we don't want any curvature to diffuse through the boundary. Even though the curvature will diffuse, we want to make its derivative 0 on the boundary points. So here we might say the derivative ks, and now I use a vertical line to mean evaluated. Evaluated at the boundary of gamma. This is some symbol that means boundary of gamma. It's the same derivative symbol, but that's just what it means. It's same symbol for two different things, is 0. So at these boundary points, you have this angle condition, and the derivative of the curvature vanishes. That's these. Now, before I stop, I know I've gone a little bit over time, but before I stop, I would like to just explain a little bit more about the energy of these equations. So we'll shrink that down a bit. It is like black magic, isn't it? And we'll just write a little bit over here. Okay, so for the free elastic flow, I talked about the total bending in L2. We'll write this down. So we call this E for elastic or Euler. So we should also mention this is Euler's elastic energy, famously considered by Leonhard Euler hundreds of years ago. It's 1/2 times the integral of the curvature squared with respect to length. All right, so you integrate. Integration, if you don't know what that is, you're just adding up things continuously along some kind of fixed path or fixed region. So here we're adding up the quantity k squared all along the curve, and we call that the total energy, total bending energy, it's called. And the free elastic flow has this property, and this is really the gradient flow property. For the free elastic flow, you have that as time changes, the time derivative of this energy is minus the integral of the velocity squared. So later on I will call this velocity f because it comes up a lot, but here I'll just write it down. Now what this means, a squared number is always non-negative, and minus that always non-positive. So what that means is that this flow, by its design, for free, reduces the total bending. So your curve should become less bendy over time. Straighten out, get stretched out. Okay. Now, can I justify also my other comment? Yes. So for the curve diffusion flow, we have property for the length. Okay, so if I differentiate the length, by the way, the length is just the integral of the number 1, right? So just integrate ds, integrate the number 1 along the curve, and that'll give you the total length because you're just adding up 1, 1, 1, 1, 1, 1 all along the curve, give you the length. Okay, and now we work out L prime, and we get, so L prime is just a shorthand for ddt of L. Sometimes the primes are just quicker to write, more neat sometimes. And what we find is that this is minus the integral of the first derivative of the curvature squared, ds. Now, if you look at the actual velocity here, the velocity is kss. So it's not the two derivatives of k, but just one. So in a way, you've reversed differentiation in this quantity, and that's why you get this terminology h minus 1. But it's not really h minus 1 because h minus 1 technically is a different thing, but morally you say h minus 1 because you've removed one derivative from the velocity, from the normal speed. Okay. I think that's all I wanted to say for this one. I'm sorry I went a bit over time. I'll try not to do it again. But yeah, I hope you learned something, and I'll see you in the next one. Okay, peace.